Welcome back to Software Engineering 2FA3, Discrete Mathematics and Applications 2. My name is Bill Farmer, and today we're going to be talking about push-down automata. In preparation of this, we need to talk about stacks a little bit. There's two ways of thinking about stacks. You can think about a stack as a value or as a machine. And we're going to start by thinking about a stack as a value. So we're going to think about it as a number as a value, or a sequence of integers as a value, or a matrix as a value in that sense. So if we think of a stack as a value, we can define an inductive set, which we'll call stack here. This inductive set, stack, which is defined by the following constructors. There's just two constructors. There's bottom and push. And bottom is just, it denotes the bottom stack, and push is a constructor. It takes a stack and an element and then pushes it on the stack. So the idea is the bottom stack looks like this, and there's nothing on it. And then using push, we create new stacks that will look like this. So basically we have a stack of elements. Elements can be pretty much anything, and each stack is going to be a finite sequence of elements. And these finite sequences are constructed using the bottom and push constructors. Now, once we have these values of stacks, it's useful to try to access certain components of a stack. So remember, if we have a stack like this, we want to get at the components. And there's just two ways of doing this. One is pop. Pop basically it takes off the top thing and gives us another stack, the stack basically without the top thing. So pop takes a stack created by push, and it returns the stack that was obtained by pushing something on a stack. And then there's another accessor called top. Top gives you the top value. So the top of push S and AE gives you E. Now, depending on how things are defined, we have a problem when we have pop of bottom, because how can we pop a bottom stack? Sometimes pop of bottom equals bottom. You do nothing. Top of bottom is even more problematic, because if we have a stack that has nothing on it, how can we get the top element of that stack? It really has to be undefined. Anyway, the important thing about stacks are finite sequences of values, but we can only access them last in, first out. That means, again, if we have a stack of things like this, if I want to get to A1, I have to basically pop this, pop again, and then use top. That's the only way of accessing a stack. It's a very limited approach. So this is an idea of a stack as a value. We can define inductive set of stacks that are built from just two constructors. Now we can also think of a stack as a machine. And it consists of a finite collection of values of type element, and there's three options. So the first option is we take an element and we add it to the stack. That's push. Pop removes the most previously added element, and top returns as output the most previously added element. So instead of thinking of stack as a value, we think of it as basically a machine, and this machine works that I can push things onto the stack and I can pop things off the stack, and I can look at what's on top of the stack. So these may seem very equivalent, but they're actually pretty different. In the first case, we have an inductive set of stacks. They're just values. We can move from one value to another using our constructors and bottom and push, and our functions pop and top. With a machine, we have a machine that has a state, and we can modify that state using these three operations. So again, with a stack as a machine, access is done in the last in, first out kind of fashion, which is sometimes called LIFO. Okay, now in analogy to this, we of course can think of a non-deterministic finite automaton as a machine. We can also think of it as a value. Remember, when it was defined, it was a certain kind of tuple. So we've already been thinking about NFAs as both values and machines, but if we think of it as a machine, it has an input tape. This is the string that we're reading, string of characters that we're reading. It has a particular state that it's in, and it has a transition function. And as it reads, this transition function is its program. As it's reading the tape, it's moving from left to right, and it's changing state according to its program. So the tape reads left to right, and it's read-only. We can't modify the tape. The memory is finite. Essentially, the memory is just the finite number of states that we can be in. And the program is non-deterministic. Our transition function gives us options. We're not deterministically forced to do one particular thing. So that's what an NFA is as a machine. And now we're going to look at a new kind of machine, a non-deterministic push-down automata, an NPDA. It's similar. It has an input tape. It has a finite set of states. It has a program which is a transition relation, so it's a bit more general than a transition function, but it also has an additional kind of memory, which is a stack. Now, a stack always is a finite amount of memory, but it has unbounded capacity. So normally we think of this as a kind of infinite memory. We can have as much of it as we need. But the thing is, this is not ordinary infinite memory, because we can only access this memory according to the rules of a stack. So that means if we want to look at something like A2, we got to pop everything off of the stack above A2. Then we can use top to look at A2. So this tape we read it left to right. It's read-only. The memory is unbounded but accessed as a stack, and the program is non-deterministic. So this is very much, as a machine, an NPDA is very much like an NFA, except we have the stack, and it's unbounded, but we access it in the stack-like way. Okay, so now we can define a non-deterministic automata mathematically. It is this long tuple. It's similar to an NFA or a DFA, but it has more structure. So it has a finite set of elements called states. That's the same. It also has a finite set of symbols called the input alphabet. That's the same. It has a finite set of final states. It has a start state. And it has another alphabet, which is the stack alphabet. these are going to be the elements that are put on the stack. So they come from their own alphabet, which could be the same as the input alphabet, but they don't have to be. And there's initial stack element, so that if you think of this as a machine, the machine always starts with an initial stack symbol, which we'll represent as the bottom symbol. And it has this transition relation. So the transition relation relates a triple, which is a state, an input symbol, or the empty string symbol, a stack symbol, and it relates that triple to a pair of a state and a string of stacked alphabets. So we're going to show you just in a moment how this works. There's two cases. The first case is we have a state, we have an input symbol, and we have a stack symbol. And in that case, what this means is if we're in state P and we're on our input tape, we're reading an A, and a little a, and capital A is on the top of the stack, then what we do is we pop that A off the stack, and we push on this set of symbols onto the stack. So we push BK, then BK minus 1, and so forth up to B1, and then we move to a new state, Q. And on the input tape, we move one step to the right. So that's what normally happens. But there's another option, is that instead of having an input symbol here, we have epsilon. We do basically the same thing. We're going to be in state P. We have epsilon here, and we're going to have a stack symbol here. We'll pop that off. We'll push on, so we'll pop off A. We'll push on this finite sequence onto the stack. And then we'll enter state Q, but we will not move the read head. So basically, this kind of transition works just like this transition, but we do not move the read head. Here, we're reading A, and then we move one step to the right. So we can say a configuration then of one of these machines is it's the state we're in, it's the string we have yet to read, and it's the contents of the stack. That's a configuration. So as the machine is working, we are going from one configuration to another. So this is a current state, the unread input string, and the stack contents. And the start configuration is always this form. It will be whatever this is. This is the start state. And this is the current unread string. And this is the start stack symbol. The start stack symbol can be whatever you want, but we represent it by this bottom element. And now we can define the next configuration relation, which takes us from one configuration to the next configuration. And basically I'm repeating what I already said about how the machine works. So if we're in this state and we have this pair in our transition, so if we have this pair in our transition and we're in this state, then what we're going to do is this configuration, we will move, well, let me back up. If we have this in our transition relation, and we're in this configuration, then we will move to this configuration. So if we're in state P, we'll go to state Q. If we're reading the string AY, and we have A up here, we will, in the next configuration, we'll be reading Y. If we have A on top of the stack, we will pop that off, and then we will push on this. So this is how a transition goes from one configuration to another in the first case. But we also have the next configuration relation when instead of having an input symbol, we have epsilon. So if we're in this configuration, we will move to this configuration. So basically, if we're reading Y, if we have a string Y, we're not going to do anything. That will stay as Y. But the rest is going to be similar. If A is on the top of the stack, according to this, we'll pop it off, and then we will push gamma on top of the stack. So that's how the next configuration relation works. And from that, we can define basically going from one configuration to the next in n steps or any number of steps. So in 0 steps, we don't do anything. We stay with the same configuration. For n steps, that's defined as, or I should say n plus 1 steps, that's defined as taking n steps. Then we use the next configuration relation to do the last step. So this is a recursive definition. And then star just means we can go from C to D in n steps. And it's worth noting that this star relation is the reflexive transitive closure of the next configuration relation. Okay, so one thing you might be wondering about is, well, how do we accept a string? Well, there's actually two ways of doing this. So remember, we're going to start off in the start configuration, and we're going to accept this string x if we end up in this configuration where Q is a finite state. So if we process the whole string, that's why we have epsilon here. If we process the whole string and we end up in a final state, we will accept that. And that's called accepting by final state. And we can talk about the language that the machine will accept by this way of acceptance by final state. Now, there's another way of accepting, and that is acceptance by empty stack. So here we start with the initial configuration, and then we're going to go to this configuration. And the important thing here is that because we have epsilon in the second part, it means we've read the whole string. And because we've had epsilon in the third part, that means the stack is empty. And so if we read the whole string and we end up in a state where, or a configuration where the stack is empty, we will accept. That's called accepting by empty stack. And we can talk about the language of the machine that's accepted by this method of acceptance. Now, you might wonder how these two things relate to each other. They're related by what I'm calling Theorem 9. If we have some language over an alphabet sigma, then that language will equal the language that's accepted by final state for some NPDA M1, if and only if it's accepted by empty stack, by the empty stack acceptance criterion for some NPDA M2. So basically, what these machines will accept are the languages that these machines will accept are the same regardless of what kind of acceptance you use. So if you have a machine that accepts a language by final state, there will be another machine that will accept that exact same language by empty stack and vice versa. Okay, so now let's look at an example. Here's an NPDA. Everything is defined. Notice we just have one state. We have just left and right parentheses for our input alphabet, and for our stack alphabet we have the initial stack symbol and we have the left parentheses. And delta has just the following transitions. So notice we have only one state. We never leave that state. If we're looking at a left parenthesis, we will push that onto the stack. If we are also looking at the initial symbol, if we're looking at a left parenthesis on top of the stack, we will also push that left parenthesis. If we're looking at a right parenthesis and there's a left parenthesis on the stack, we will pop off that parenthesis and we won't push anything more on the stack. We'll just pop that off. If we're not looking at anything, we're done with the string, and we're on the stack, we have the initial symbol, we'll pop that off. That's it. That's the machine. So let's see how this works. So this machine is going to accept by empty stack the set of balanced strings of parentheses in sigma star. So we've already talked about this language. This language is context free, and M is going to accept that. Let's look at some examples of how it works. So the first case is M will accept the empty string. We start off with the initial configuration, the start configuration. We're in state S. We're not reading anything, and which is going to be the empty string, and we just have the stack symbol, and we will go to this configuration, which is the final configuration by acceptance by empty stack, and we're going to use this transition. If you are wondering where that transition came from, it's right here. It's number 4. So we use number 4, which says if we're done looking at a string and on the stack is the initial symbol, then we will stay in the same state, but we will pop this off and put nothing else on the stack, so the stack becomes empty. So that's the first example. Second example is it accepts this string, and you can see easily that this string is a balanced string of left and right parentheses. So here will be the start configuration. We only have one state. Notice nothing happens to the states. We have one, we're in the single state. Here's our string. Here's what's on the stack. And then what we're going to do is we're going to be reading this, and we use then this transition, which says if we're reading this and we have this, then what we're going to do is we will pop this off, and then we will push the left parenthesis and the initial symbol. So we will get this. So it looks like what we did is we just popped off, it looks like we just added the left parenthesis, but really technically we popped this symbol off and then added both the left parenthesis and that. And we moved away from this, so now we move one to the right, so now we're looking at this. We do the same thing again, and we end up, well, actually we don't use the same thing again. Now, on top of the beginning of the stack is this, so we're going to be looking at this. This is on top of the stack. We pop that off, and then we put 2 back on, and we get this. And then we have moved to this. Now here we have a right parenthesis, and so what we're going to do with the right parenthesis is we're going to use this rule. So we have a right parenthesis, we have a left parenthesis on the stack, we pop off the left parenthesis on the stack, and we don't push anything else on it, so we get to this. And then we do this rule again. We push this down here, and then we use this rule again, and we effectively pop off these things and get to here. And then we use the rule we saw up here, because we're not reading anything more, we can pop this off, and then we end up in the configuration we want. We've read the whole string, there's nothing there, and the stack is empty, so we accept that string. Okay, so this is how this machine works. Okay, there's one more thing we want to do today, and that is here are some configurations that M could be in, and some of these are configurations that M will be stuck in. So if M gets into a configuration that will be stuck, it won't be able to accept the string. And remember, M is going to accept the string if there is some configuration that accepts the string by empty stack. Okay, so I'll give you a moment. Think about these configurations and identify which ones will make M get stuck. Okay, welcome back. Let's go through these one by one. So the first one is we have a string that begins with a left parenthesis and our stack is empty. What can we do? Well, actually, we can't do anything, because if you notice these transitions, we have no transition when the stack is empty. So we get this, we're going to get stuck in this case. The next one is we are looking at a right parenthesis. That's the first symbol in our string, and we have an empty stack. Same thing, there's no transition to help us here. The third one is we're looking at a right parenthesis, it's the first symbol in the string, and we have the initial stack symbol. Well, let's see what we can do there. Well, there's two possibilities. We have an initial stack symbol here, that's with the left parenthesis, and here we have initial stack symbol where we have epsilon. There is no transition when we have a right parenthesis. So we also get stuck with this. And the fourth one is the case we don't get stuck. If we have a right parenthesis that starts our string, and on the stack is a left parenthesis, we know what we do in that case is we pop off this left parenthesis, and we don't push anything more onto the stack. Let's just go and look at that transition. That's this transition. When we're reading a right parenthesis and there's a left parenthesis on the top of the stack, we pop that off and we don't push anything on. Okay, so that completes, went a little bit too far. That completes what we're going to talk about today. As you saw, we're going to continue with another example next time. Thank you very much.